Thank you for coming to today's seminar. We have it's an absolute pleasure to introduce you Guillermo Garcia Segura. He got his PhD in La Laguna in 1994. Actually, he graduated here at Granada University first and completed his PhD in the Department of Astronomy of the University of Illinois at Urbana-Champaign. And since 1995, so that's 30 years now, he has been at the Institute of Astronomy of the National University of Mexico, where he's senior research fellow. He's been a pioneer in the field of hydrodynamics of the circumstellar medium around massive stars, and the first to calculate the formation of green nebulae around large stars and luminous blue variables, taking into account stellar evolution with calculation coupled with the hydrodynamics. This calculation had a significant impact in the field, and particularly for the study of supernova interaction with the surrounding medium, as well as the formation of afterglows in long gamma ray bursts. He's been an advocate of including magnetic fields to understand the shaping of planetary nebulae, since they cannot be reproduced without magnetohydrodynamic calculation. He supervised for doctoral thesis, including that of Eva Sobrino, who is currently the deputy director of the INC and won the SIA award for the best doctoral thesis in 2002. So, absolute pleasure to introduce you, Guillermo, here and to learn about jets in planetary. Thank you very much.
Well, thank you for this opportunity. I thought that the talk was going to be in Spanish, but anyway, it doesn't matter. So we're going to talk about planetary nebulae in a completely different way that you probably understood in the past. And you will see now what the difference right now. Everybody knows what a planetary nebula is. It's a circumstellar nebulae, which has all kinds of lines, emission lines, and so on. And depends of the mass of the progenitor. Probably you can have different, or at least what we understood in the past, you can have different morphologies. You will see that we were wrong. The classical view of a planetary nebulae formation is that, for example, for the sun, you have the main sequence. Then when you run out of fuel in the core, you have a red giant phase that loses a lot of mass and then becomes a white dwarf. And you, in the red giant phase or the AGB phase, you have a lot of a very dense wind, which I represent here. And then when the central star emitting photoionization and a stellar wind start to sweep up the gas. This is the idea that we had in the textbooks in the past, right? Let's see if this is still the understanding of the community. Then we are going to talk also about jets. Jets is a English name that comes from the French jetty, I think it's pronounced jetty. And the meaning is to launch, to take off or something like that. And actually comes from Latin, is jactare, is to throw away, something like that. In general, a jet is what is understood in the air for many people is a liquid or a gas which is forced in a nozzle, so it has a much higher velocity, right? Like the hose of a garden and so on. Or in this case, the engine of a jet plane. That's why it's called jet, right? But in astrophysics, of course, this is different. We don't have a nozzle like in the case of a garden hose. We will see that we have a accretion disk This accretion disk is going to launch a magnetic wind that is going to be collimated and is going to form the jet. So the nozzle in this case is some kind of magnetic field which forces the gas to collimate to the axis. We have radio galaxies, we have jet formation stellar formation jet. In both cases, you can see the jet is coming from the central object very nicely. You see many pictures, but this is not, or at least this is not what we saw in Planetary Nebulae at the beginning. That's why it's so strange. I will show you later cases where you can see the jet coming from the source, but it's not. There are only a couple of examples. Jets in general has an all scale the same behavior when you do it in theory, magnetohydrodynamics or hydrodynamics. They have very different, very similar condition, very similar equation, but in this case, a couple of meters, this is a couple of almost a parsec. So, but you can treat jets almost uniformly in the whole universe. In this case, for example, this is I like this picture a lot. Is the HST picture of HH30, and here you have the ALMA observation on CO, where you see the red and the blue. So the disk, you see perfectly this rotating. So in general, in astronomy, jets are collimated flows, but are supersonic. That's the difference with the Earth. For example, in the Earth, a water jet is not supersonic, a lava jet is not supersonic. The engine of a rocket of a jet plane is supersonic. In the case of astronomy, all the jets are supersonic. Okay. Then we are going to talk about Planetary Nebulae and looking for jets. And historically, this was the first case in '85. It was the first discovery of a jet. This was discovered in ultraviolet in the carbon-4 line. And people was talking, how are you talking about a jet in a planetary nebula? That's very weird, it's very strange. Then later, actually, Luis Miranda and Solf found also another jet in the Eskimo Nebula. But this is a picture of the 80s, and this is a picture of the 90s with the HST. But you don't see the jet. I mean, in the optical, you don't see here anything that looks like a jet, right? We have these clamps, they have cometary tails, but you don't see the jet actually. 30 years later, Martin Guerrero, with the Megara in the GTC, they found that the jet actually is here. It's a very wide, fluffy jet. It's not thin. Actually, you can see it from the star, but also could be because of the thickness and the projection. Anyway, it's not the thin jet that we see in Heavy-Haro objects or even in extragalactic forces. The second case was in 1990. It was the ICAT Nebula. This is a picture of the 80s. You almost see something here. In spectroscopy, you can see here high velocity wind, high velocity gas, also by Luis Miranda. In the HST now, in the 90s, we can see clearly a jet over here, and the other, which is tilted here. But again, we don't see the jet coming from the source. Right? This is very strange. So, are we talking really about jets? Jets in Planetary Nebulae, jet in the sense of Heavy-Haro object or AGNs? We'll see later. In the 80s, the idea is that these called jets, they thought that they were formed like the hose garden, like you have a nozzle, which is the peak of the nebula, which confine the wind and form this globe or jet. That was the idea, okay? another case that they thought in the past that this is coming from the collimation of the nebula itself. It's called the Jorge Cantó model. This is basically the idea that you have a nebula and the gas collide. You have a gas that collide and goes to the polar regions and form these blobs. The problem with this kind of idea is that this gas is hot. It's 10 to the 6 Kelvin. The sound speed is of the order of 1,000 kilometers per second. And there is no way that you can cool down and put high density in the polar regions to form jets or blobs. Actually, all the simulations, they never found blobs or jets. You have to have very low velocity of the wind of the order of several hundred kilometers per second, 200, 150, which when they collide, they have 10 to the 5 Kelvin, which are very relative. In those cases, probably you can find it, but not when you are in the region of 1,000 kilometers per second or 10 to the 6 Kelvin. So the idea, it was not the best idea that the theoretical people had in the past. This is an extreme case, it's Fleming 1. You can see here the jet coming out from the star. Also, you can see here, there is like a cavity that is focusing the gas. But imagine this gas, this jet is precessing. You can precess a water jet from your garden house, but you cannot do that with the nebula. You cannot do with the nebula. Now let's point in that direction. Now let's point in that direction. It's impossible. It's obvious that the source that is precessing has to be in the center. Like we know that now there is accretion disk, but at this time we didn't know, right? Another case is the hourglass nebula, which when you see in high exposure, you have blobs up to here that they go up to 500 kilometers per second, which is 10 times the expansion velocity of a normal planetary nebula. So people was really confused. So they couldn't explain why you have these high velocity gases. Another case, this is quite ugly, but it's like a, anyway. So the accretion disk, are we talking really accretion disk? At those times in the 80s and 90s, we didn't observe any accretion disk in a planetary nebula. We knew about accretion disk in nova, in cataclysmic variables, in all kind of almost closed binaries, no? But there was no good signals about accretion disk in planetary nebula. Even more, binaries at that time, there was only a few, maybe 10 closed binaries. So there was not too much chance to understand what was going on those times. So one idea that came from supernova remnants that started with Martin Rees studying the Crab Nebula, then Begelman and Lee, and Chevarly and Luo, then Rafik and Franco, and then myself, was what happened if you have a magnetized wind instead of accretion disk, I mean the stellar wind with a magnetic wind, then you can do the same stuff, which is in a long scale, you can collimate that gas and form jets, okay? Without the need of an accretion disk. The problem, well, there were many problems, we will talk later. So, but this idea was really working. I mean, you have this gas coming from the star, has the reverse shock, and then the magnetic pressure is so important that dominate the dynamic of the nebula, forming jets over here. Okay. The idea was at that time, we're talking about 95, 96. Now, if you have a star, and probably with a binary, the star can precess. So when you launch the wind with the magnetic field, the toroidal magnetic field, which is responsible for the collimation, is going to point always in the direction of the rotation axis. So in this time, and this, I mean, with this model, you can precess your source, you can precess the formation of the jets, and also appear skin instability, sausage instability, many things that we were playing, very exciting. In another paper by myself, we did all kind of simulation with, we could reproduce basically all the morphology in planetary nebulae. Actually, the confirmation in this nebula by masers of water and OH, they found the magnetic field and they found that they are toroidal and so on. We thought that we were in the right path, in the right way, even to simulate this complicated nebula, right? But, this is a very big but, when the protoplanetary nebulae with the younger phases of the PNs, the planetary nebulae, start to appear with HST, most of the protoplanetary nebulae were very elongated, extremely elongated, like this case, right? Actually, this case is the first one that shows a jet coming from the source. And this is a disk. It's not an accretion disk, it's an excretion disk, but we will see later. But the real problem was that when these nebula were observed in CO, for example, using the 30-meter in picobelletta, they found that to explain the expansion velocity and the momentum of the nebula and the kinetic energy of the nebula integrated in time, the star by photon, by the momentum of photon, cannot explain the momentum of the nebula and the energy of the nebula. It's 10 times larger what the light can provide. So we have a deficit in the energy to form the nebulae. So the star by radiation cannot form it. We know that if we have accretion disk, the reservoir of energy, gravitational energy, can be transformed in kinetic energy, right? We know that. But at this time, it was hard to explain in the context of planetary nebula. This is another nice example that you have an excretion disk. Why excretion? Because this is very big. We are talking almost in the order of parsecs, no astronomical units. And you can see here the gas collimating and forming this block. By the way, this is the velocity here is like 1,300 kilometers per second, extremely high. Impossible to understand with a normal in the context of planetary nebula. And this is, for me, what is called now the textbook nebula. It's a water fountain, W43A. This is made with ALMA. It's only half 60 years old, this nebula. And you can see a perfect jet here of CO. This is seen in CO, the blue. We cannot resolve the accretion disk, but has to be there. I mean, there's no doubt. Has to be an accretion disk there. Eh? The whole size is like the solar system, 1,000 AU, something like that. This is another case which is called the Calabash Nebula, has 900 years old. This is an HST image. What you see here is reflected light. And almost all the gas there is molecular. You can see in CO, the whole gas is very cold. And what you see here is the reverse shock of that gas colliding, not the outer shock, it's the reverse shock. And this is H alpha. It's emitting by collision. So the accretion disk has to exist in the planetary nebula context. I think there is no doubt now. And an accretion disk can solve the problem of the energy budget. We have a lot of energy stored in an accretion disk that you can compress and eject this kind of winds and jets, okay? And actually, they are very powerful. They are 10 times larger than the photon of the star. So we know how, for a long time, how more or less how accretion disk works in binary stars. This is the typical case. an accretion in the binary. We know for a long time the magnetic lines are doing like an espiral. This year has been confirmed by radio observations. Very nice study where you see a helicoidal field coming with the jet. So we have mainly three scenarios that can form a jet in planetary nebulae or in protoplanetary nebulae. The first one is when you have a big separation in the binary, and the secondary star is capturing or accreting the gas of the wing of the AGV. This is like a very soft stage. Maybe you can form here jet, but probably the density and the mass involved in the accretion disk is not too big, so the jet maybe is very weak. I would say it's of the order like a nova. In a nova, you don't see a jet, probably. In the second case is when they start getting closer, and then you reach the Roche-Low overflow. In this case, the amount of gas that goes to the secondary is enormous, it's huge. And then you form a big accretion disk, and in those cases, you really can form a very powerful jet. But the time is limited, because very soon it's going to reach the common envelope phase. In this phase, the star is going to be captured by the primary, and it's going to do a spiraling. And at the end, what you have is a binary, a closed binary, orbiting each other with an accretion disk outside, right? But this is an accretion disk of two stars. It's a circumbinary disk, okay? But the idea is the same. You have a stationary wing there, it's rotating around and wants to accrete. In this phase, the density and the mass of the disk is very important. So you can launch a jet here. It's going to be very massive and very energetic. That's the idea. This is how it's done, the spiraling of a common envelope. And all the gas is ejected mainly in the equatorial region. This is looked from the pole. This is another view from the side. This is common common envelope is very important even to understand the fusion of black holes, neutron star, and so on. The common envelope is important in the whole stellar evolution, not only in planetary nebula. So the idea is that when we have the common envelope, the whole gas that is ejected, now we are going to, in 3D, this is a 3D problem, it's very, very time consuming. You need hundreds of hours supercomputing to compute 100 days of physical time. So there is no way that we can evolve this system to 10,000 years, right? So we have to do another approximation. In this case, what I did was to catch this simulation. I do a average in the phi in spherical coordinates, and I'm going to compute the rest of the evolution in 2 dimensions. So we have r, the radius, and theta, right? In phi, I assume that it's symmetrical. So now it's going to be the expansion in 2 dimensions. The good thing is that in this way we can expand the grid like a Hubble law, and so we can follow the evolution of the gas from the star in 1 AU or less to parsecs, 5-6 order of magnitude, and we can do it in amounts, something like that, not in years. So here you can see that the result of this common envelope evolution, you have 75% in this case is bound gas that cannot escape from the system, but 25% of this gas is unbound. This is the gas that is going to leave the system. It's hard to find a computation that unbound 100% the gas. Most of the gas remain and is going to form. This is the gas that is going to form an accretion disk. We will see later. Then we include a magnetic field, which is not important in the dynamic. It's only 5% of the equipartition value. So the gas is important, not the magnetic field in this phase. This is the gas, this is the magnetic field generated in the transition from the core and the envelope inside of the star. That when the star is eject the envelope, the gas, the magnetic field is going out with the same envelope, right? So now what we are going to do is the next exercise. With this simple approach that is one star go inside the other and form the ejection of the envelope, starting from this simple principle, we are going to do step by step, and let's try to arrive to a big planetary nebula, step by step. So in different chapters. So first, to see how is the formation of the disk. We have here the inside is the binary, the closed binary is rotating. So we have is the part that is bound gravitationally collapsed in an accretion disk. And this accretion disk, this is of the order of, this is 1 AU. The Earth is like here, this is like Venus, this is like Mercury. So the period here was 2 days, only 2 days to start. So this is what you have after the common envelope. Then we are going to see what's happened with the evolution of the disk that is formed. And what we are going to see is how the magnetic field is going to eject the gas mainly by magnetic pressure. Here I'm going to show you a movie. It's 10 images per day. A physical day is 10 images. So here is called, here what we have is a small, tiny fraction, like 0.5% of the toroidal field that produce small bumps and produce poloidal field. And this poloidal field is the one that can do the accretion, because you need to have torques in the accretion disk to produce accretion, because if you don't have a radial field, a radial magnetic field, you don't produce the accretion. Okay, you need something to slow down the gas, and it's like putting a leg in the bicycle. You need to stop the gas, right? So this is called magneto-rotational instability, or the valgus instability. And basically, what you produce is the gas from this area is the one that loses angular momentum and collapse, and the angular momentum is transported in the equator outside. So it's like there is like a flow of angular momentum there. And as you can see, once that the accretion is very important, the toroidal magnetic field start to launch very fast. We call, actually this model is called the plasma gun. It's like a gun. It's like you are shooting blobs of gas. First, this is magnetic pressure, poor magnetic pressure. And then when the magnetic field becomes very close by and very intense, you produce this plasma gun and start to producing pinching in the axis of the gas that launch this gas in very high speed. As you can see here. This is good. Boom, boom, boom. Some kind of a very fast wind, 300 kilometers per second. The kilometer per second is because here is more, I mean, it depends on the escape velocity of the accretion disk in the inner radius, right? If you have only a single star, in the binary case, for example, a main sequence star, the main sequence star has 500 kilometers per second, like the sun, the escape velocity. So your jet is going to have like the order of 500 kilometers per second. But in this case of the binary, you have 150 kilometers per second the escape velocity. So the jet that you form is going to be of that order. So as larger you produce the binary and the accretion disk in the inner radius, the slowest is going to be the jet. If the accretion disk is very close to the both stars, for example, 1 hour, I mean, 1 hour it can form also a type 1a supernova when the two white dwarfs are larger than the Chandrasekhar mass. Anyway, those jets are going to be very fast. So it depends on the inner radius of the circumstellar accretion disk, the circumbinary disk. So what is going on here? Well, you have seen that this star, they produce like a gap, like a vacuum. And what you have here is like a beater, with a mini pimer. You have something that is ejecting the gas by centrifugal forces. And what you produce here is a centrifugal barrier. It's very hard to cross that barrier. You have to go through the Lagrangian points to be accreted. So in this gap, what we have here is a centrifugal barrier. And if you have now here the valence instability and it's trying to collapse on the gas and accrete on the gas, when you push that gas, it cannot go to the star, so it's going to blow up and down the centrifugal barrier. That's basically the idea of the launching of the wing here. And this gas is going to be collimated later by the magnetic field, the toroidal magnetic field. So now again, now that we see how is the magnetic field working here and the gas ejected here, what we do now, I'm sorry. What we are going to do is, now that we see the wind coming out in the external boundary, I take this wind coming out from the grid. I'm going to introduce this wind in a larger grid, okay, in the inner boundary. So here is the inner boundary, okay. That gas like blowing out in the model of the ejection of the gas is going to be inserted in this model where what we have here is the ejecta of the common envelope, the ejecta, the unbound gas that was escaping through the polar region, through the equatorial regions. Now, if I introduce that gas injecting this is going to happen. It's going to form a very nice jet. And this is the beginning, the formation of a protoplanetary nebula, because still it's not photoionizing. The star inside, the central star, still is not hot enough. It still has a lot of gas around. Actually, it's collecting more gas from the accretion. So, if, for example, 1,000 days, what we are going to have is a protoplanetary nebula already formed with a disk around, but this disk is not an accretion disk, it's an excretion disk. This gas was expelled from the star. That's what we see in many pictures. It's a big disk, but it's not an accretion disk. It's coming out, the gas. So we start working with different models, like for example, this, I don't see the name here, H10158 is the telephone number. So let's see if this works in the oh, sorry. So we start trying to reproduce observer nebula with ALMA. This is our first case. Actually, you can see here the simulation, and this is the ALMA reconstruction. It's really nice how the wind is. In this case, it's a very light wind coming from the disk, but they actually get focused by the toroidal field. We were not so wrong in the 90s. I mean, this is the idea. The wind coming, we didn't know it was from the accretion disk, but there was a wind, a magnetized wind coming out and then producing the jet. So the idea was fine. The problem was the source. The source was not the star, was the accretion disk or the circumbinary accretion disk. But the idea worked. Now we see my favorite picture, which is the W43A. I mean, I think it's very impressive how well it's doing the job, this model. We didn't make anything straight, just to start coming out, the gas in the equator, the formation of the jet, and reproduce very well most of the things from the nebula. This nebula around is swept up by the wind, the jet inside. This is a two-dimension, I don't see here the blobs, but in 3D, the kink instability and the source instability will form blobs. In these blobs, no? This is a magnetic effect, it's an instability. In the case of Calabash Nebula, we have the accretion disks forming what they call fishbowl, the reverse shock here, this is the outer shock. So it's explained very well all the feature and the dynamic of most of the protoplanetary nebula. For example, the formation of W43A is like this, more or less like now it's 60 years old, can reproduce the nebula, and this calculation goes up to 1,000 years old. This is 1,000 years old. It's a protoplanetary, basically. In the case of the Calabash Nebula, this is the model how it worked, and it was working quite well also. It's very small, the accretion disk and so on, so it's here inside of the, we cannot resolve it. But remember that these grids are expanding. So we start from a small grid, like with very high resolution, and then what we do is to catch the shock, the outer shock here, and this is what, with the shock there, we expand the whole grid, like a Hubble Lemaitre flow. So now we could form a protoplanetary nebula. Perfect. Now, can we form a planetary nebulae that come from a protoplanetary nebulae, or are different sequences? This is another idea, that protoplanetary nebulae is one kind of object, and another kind of object is planetary nebulae, because most of them, they don't look like each other. You see a protoplanetary nebulae that is like very narrow, like a jet structure, and you have a planetary nebulae like the Helix Nebula, like the Ring Nebula. They don't look like, the same, not completely different. So the idea is, are two different kinds of objects, or we can go from one to the other. This is what we are going to see here. For example, let's take the W43A, which has 60 years old, and let's see if we can go to a planetary nebula like the Red Spider Nebula in the southern hemisphere. The idea basically is, this is the computation of this model at 1,000 years, and then we are going to evolve this nebula 9,000 years more. But now, instead of including the wind coming from the accretion disk, we assume that the accretion disk is already gone, it cannot survive forever. And now we are going to use the wind coming from the central star, the wind and the photoionization, because it's obvious that the accretion disk, once that the gas is accreted, is going to disappear. And then the stars start to be very hot, very bright in UV. It's going to ionize everything around, and it's going to form line-driven winds. Okay? So this line-driven wind is the one that we are going to inject now in the center of the grid. And we are seeing the evolution of the gas. It's coming. Yeah. It takes some time. It's 10,000 years. So this is how the wind from the central star is coming out. Of course, there is a very dense material in the equatorial places, so the wind cannot go to the equator, has to be only go to the polar region. You see now, you have this Kelvin-Helmholtz stability and so on, that very close by to the red giant, to the Red Spider Nebula. So this is basically the idea that, yeah, you can form a planetary nebula, at least a bipolar planetary nebula, very easily. And you see that there is a huge amount of gas here, and you see why it's so bright. The core of this nebula has a lot of gas there inside, very close to the star. In this paper in 2022, we could reproduce, almost many features of many planetary nebulae on these blobs and so on, of bipolar, general bipolar, but also changes overall the binary separation, the final binary separation after the common envelope. You can reproduce very nice also elliptical nebulae, not only bipolar. So basically, the most important effect is going to be the separation of the binary, and then later the mass of each star. So I think that in the binary scenario, you can reproduce most of the planetary nebulae. So, conclusion, the jets that we observe in planetary nebulae must be formed early in the protoplanetary nebulae phase. Later on, they start to disappear by photoionization and so on. So in some cases, what we see is the remnant of the protoplanetary nebulae jets that formed before. Thanks to the jets, most of the community now think that most of the planetary nebulae that we observe, at least the very nice one that we see, the Halley Nebula, the Ring Nebula, and so on, are coming from binary interaction, not from single star, because there are many features that cannot be explained by one star. For example, the Southern Ring Nebula, which was the first one that the James Webb did the study, there are four stars involved in the planetary nebula. A binary that is visual, you see the central star and one A star, which is in the main sequence. Then there is a pattern in the nebula that we think that there is a 40 astronomical units in the binary that produce this kind of rings around, and then the central star was a common envelope star. So there are 4 stars in total to explain this kind of. In the case of the Sun, of course, it's going to depend on Jupiter. Jupiter has plenty of angular momentum, and it's going to do a lot of damage if the Sun can catch it. If they don't interact with each other, the nebula of the Sun is going to be quite boring, probably spherical. But if Jupiter goes inside in a common envelope, it's going to change completely the evolution of the nebula in the future. So just to finish, Alberto is not here. He's doing the proposal today, the deadline of the proposal for IER, Artificial Intelligence. But anyway, I want to thank him for this sabbatical here in the Institute and also in La Mayora, where I have been most of the time in the sabbatical time. So thank you.
Thank you very much, Guillermo. Do we have any questions?
I hope I change your mind that planetary nebulae is not like in the textbook. It's for completely different.
Okay, please.
In the simulation, the material that is being launched from the disk, the velocity is different. Is because the material is being launched at different radii.
Right. The one in the center is faster, just because of the schedule.
There is also a velocity variation in the.
Yeah, well, it's accelerated also by pressure, so there is a limit for the velocity. And it goes from subalbenic to superalbenic in the transition.
This variation can be related to accretion variability. Or...
there is also variability, of course. This is not stable. This is chaotic, actually, because you know the 2 stars orbiting. You have seen how different is the accretion to the Lagrangian point and so on. So this is very weird, no? That we're making blobs and so on. So it's not stable.
Maya, please.
Thank you for the nice talk. That's remaining the Mexican thought because with a lot of context, which made the audience enjoy a lot. I have actually two questions. The first one that you have mentioned in the last simulation that you have to inject a lot of wind to explain the different phase from planetary nebula to planetary nebula. But my question is, have been these winds that you have injected in this simulation have been observed?
Oh, yeah, sure. There are many PCD profiles and so on. It's just light-driven wind. Normal. It's the kind of wind that O star have. The O star is very hot. Could be from 20,000 to 100 Kelvin. Sorry, 10 to the 5 Kelvin. And you have a lot of resonance lines, and then you produce PCD profile, and then you have launch winds very, very fast, actually. Several thousand kilometers per second. Or, I mean, planetary nebulae are always stars.
And my second question is related with the accretion disk. But you have mentioned one case when the disk is expanded or the material is expanded. How do you explain this? Of course, I had in my mind accretion disk always has a Keplerian rotate, but in this case, in planetary nebula,
We have the two cases. The inner part, which is bound gravitationally, is the one that forms the accretion disk. And the external part, which is unbound, is going to be ejected, so it still forms a disk, but it's coming out.
Got a question myself. There are many low ionization structures in planetary. Are all of those the remaining of jets, or do they have a completely different origin?
Yeah, no, the one that only, I mean, are remnant of jets are the one in the polar region that has faster velocity than the normal nebula. The one that you see around are a product of high density. They absorb the radiation and produce low excitation lines, nitrogen 2 lines, something like that. It's just a photonization effect. Actually, the blob that you see nitrogen is also a photonization effect because it has higher density. But the velocity is the one that is telling you that it's coming from an old jet.
And then another question. So the remaining of those excretion disks, you see in bipolar planetary nebulae that there are bright equatorial regions there. But is there any evidence for those excretion disks in, let's say, elliptical or bipolar with no mild morphologies?
In elliptical, I don't think so because my feeling is that they come from very low mass stars, like one solar mass. So the wind is coming very late. The photonization starts very at the beginning. So everything that you have in the circumpolar region is going to be evaporated by the photo evaporation.
So it's different time scale.
Exactly. I mean, a nebula like I don't know, this bipolar probably has 2,000 years, 3,000 years old, while elliptical nebula can have 12,000 years old. So completely different. You have enough time to evaporate the remnant disk.
Okay, but the binary interaction is going to change the time scale of the stellar evolution.
Yeah.
Matilde, please.
Well, first, thanks a lot for the. I have two questions related to the stage, the protoplanetary nebula. When you talk about precession, what is moving the disk?
Yeah.
Is it possible to keep the structure while it is?
Accretion disk can precess. Yeah.
Okay. And the only thing for me was that if at that stage most of what is happening in the plane where the disk is, then what we see depends a lot on the geometry, well, on the point of view. And so this is also observed.
Right.
So
For example, the Helix Nebula, the Ring Nebula, the famous one, are almost seen from the polar direction. So if you put, it's going to have a very a very dense material in the equator, like a barrel type. So the geometry, of course, it depends on the angle where you are seeing from the Earth. Actually, sometimes you see that a nebula is spherical, and it's a disk, equatorial disk, but it's where you are looking from the pole.
Mentioned that the accretion disks are circumbinary.
Right.
But is it possible to have circumstellar accretion disks under some circumstances, maybe depending on the mass ratio?
Yes, there is no, I mean, the only thing that can cancel the formation of accretion disk in the stars is, or the star is very hot and has already wind, or they are so close to each other that you don't have enough room to make the accretion disk. But in principle, you can have 3 accretion disks, the circumbinary and one in the 2 stars. Yeah? If the condition are allowed to form them.
Another question is about the sun. You said that its future morphology would depend maybe on Jupiter. But how can you make it with Jupiter, because it's too far away for a common emblem?
Because the AGV is going to grow a lot. In the AGV phase,
But that much?
it depends on the calculation. That's a problem in stellar evolution. Some models produce an AGV very big that is going to catch Jupiter, and in the others not. It depends on many parameters, so it's very uncertain. Because actually the mass loss rate, the AGVs and Reggie phases is the most the worst study. I mean, the mass loss rate of all stars are the best study. The red giant in general are not very understood in the mass loss rate. And all the uncertainty in stellar evolution comes from the uncertainty in the mass loss rate. Right?
Yeah, actually, the evolution of planetary system at these phases is quite chaotic. So it depends on so many parameters that either Jupiter may be launched farther away or may fall closer to the sun. So that depends on the interaction with other planets and how the star is going to use the mass rates.
Right.
Uncertain. Second, please.
Hello, Guillermo.
Hello.
I'm very glad to see you here.
He was my teacher.
After so many years already. The talk has been very, very nice and enjoyable. But I always think whenever I listen to a MHD simulation talk, etc., I always wonder how many parameters are involved in those striking, beautiful simulations, and how many of them are realistic? Because well, I know I'm in the sun. Sometimes people have relied on tweaking some Reynolds number or Random number, etc., in order for things to fit the morphology, which is in the end what you are trying to simulate. So can you comment on this?
Sure. For this type of problem where the scale is quite huge compared to the magnetic formation of the dynamo or whatever, we are using ideal HSD, so we don't have many parameters to play with. Okay. The problem when you go to very small problem like sunspots, whatever, that you have free connection, that's very uncertain, etc., etc. So when you go really want to squeeze the problem to very small scale, where all the stars appear. Overall, the reconnection is fast reconnection, slow reconnection, things like that. But in ideal, we don't have reconnection anymore.
Okay.
So at this scale, I would say we are safe.
Okay, then my second question is, how far are you from inverting the problem? So instead of simulating the morphology, going from observations to deducing physical parameters of the approach of planetary nebulae.
I cannot answer that. It takes, I think it's going to take 10 more years to really understand what's going on, because right now, still the common envelope calculation are almost starting. So we are in pañales. No?
Thank you.
I mean, even more, we don't know exactly how to eject the gas properly. If the many like the here the recombination energy of the star is going to be important or not. So I mean, still seem to understand common envelope, which is, I mean, now it's in fashion common envelope because of LIGO and things like that with the black hole. Because to have two black hole, a stellar black hole, you need to pass through a common envelope, or to form a hypernova with two neutron stars, you need a common envelope. So everybody is trying to explain common envelopes, and now it's like Planetary Nebulae is the only. It's like the small cousin, like the non-relativistic cousin in a small scale, but you see many nebulae around coming from a common envelope, and you don't see that in massive stars. I mean, when you want to study how was the nebula around two black holes, I have no idea. How is the nebula around two neutron stars? I have no idea. But from Planetary Nebulae, maybe we can solve many of these questions, because we have thousands of objects compared. That's I think why it's going to be important in the next years Planetary Nebulae work in the working Planetary Nebulae to understand in general common envelope. And also, I mean, the launching of jet, because we have in a short gamma ray bar two neutron star colliding and form jet. No? It's going to be very close to this, but in relativistic scale. So,
We have a question.
There is another question by Stavros Agnes. Stavros, can you open your mic?
it's in Brazil.
Yes. Now, hi. Can you hear me?
Yes.
Okay. I am in Greece now.
I agree.
Thank you very much for this really new point of view, more or less. I have two main questions. For the formation of the planetary nebulae after the formation of the protoplanetary, you said that the wind of the star now is governs the formation of the planetary nebulae. In this case, in your model, you take into account the slow wind and the fast wind, or only the last one?
Well, the slow wind in this case, I mean, talking about the classical model, is all the ejecta from the mass loss in the common envelope phase,
Okay.
plus the previous AGB wind, right?
Okay.
So now we are including the jet as the fast wind, and later on the central star wind like the fast wind.
Okay, that's the fast one. Okay, this is the difference from the text formation, the text point of view. And we had the question about, you said that the low ionization structure are probably the remnants of the jets. But
the flyers, only the flyers.
only the flyers, yes. But if they are the remnants of the jets which are supersonic, shouldn't find them usually at the outer part of the ionized gas of the nebula? Why do we observe them sometimes inside, or this is a projection effect?
Because it could probably be the last formation of the jet, or the last, let's say, like the final hiccup of the something like that. That's why they are no long in physical size. It's like a blob only. I don't know. Probably we have to do model like in the case of a short-living accretion disk or something like that.
The example I have in my mind is the Saturn Nebula 7W09, which is slightly outside, and this doesn't fit.
No, but
I mean,
it's in at the very end of the nebula, the blobs.
yeah, but you have you have also, if we took into account the halo of the nebula and the true size of the nebula, it's
Well, the halo is coming from the thermal pulses in ADV.
so it's a step before the okay. Several steps.
Yeah.
Thank you very much again.
Welcome. So,
Okay, do we have any other questions? Please.
Hi, Guillermo. Thank you for the very instructive talk. In your magnetic simulations, you are talking about blocks or something like this, or magnetic instabilities. Jets are usually characterized by what we call knots.
Right.
I think it's the same idea, more or less. And we are favoring theories like the one of Alderraga and so on, that these knots are produced because of velocity variations in the jet. So the jet has a velocity, and then the velocity increases and catches the previously ejected material, and it squeezes out and there is a lateral ejection that produces a minimal shock that looks like this. Can your model also include this kind of velocity variations, or these magnetic instabilities produce this independently? So, I mean, your model excludes this other interpretation, or are both compatible?
those are compatible. You can both several ejections, so you have different ejections and you have both shocks, like Alex Raga. When you have a steady ejection, you still have the gloss from the magnetic instabilities. In my case, I cannot include it because I didn't include what I studied the ejection by itself. So I didn't. The difference with Alex Raga, for example, you inject different velocity and you can do it, inject it. But in this case, the question was to compute the ejection of the gas by itself without making anything. So a different approach. This is really a launching problem. But in a general case, yeah, you have, for example, if you are accretion process changing time, probably you have different accretion phases and with different velocities or whatever. So it's nothing steady here. It's pretty chaotic.
And you envisage some way to distinguish between these two
Yeah, Max,
possibilities?
I think that when you have different velocity of the ejection, you will form both shocks. When you don't have both shocks, probably the blocks are coming by instabilities, sausage instability or king instabilities.
Okay.
The king instability is the one that later on is going to break the collimation.
Okay.
Basically.
Okay, thank you.
Sure.
You might have kind of some explosive event, so a launching of a jet which is broken into different pieces according to the velocity. Because sometimes you see the jet, and the velocity depends on the distance to the source. So the farther away, so it's faster. And so if you determine the dynamic time escape, it's the same for the whole jet. So it was an event which is very short in time, but depending on the specific of the velocity. So it expands.
Actually, the jet is called pointing flag dominated, or the one that accelerated by pressure, actually has this structure like Hubble, the metronome, has faster velocity. But at the end, you get like asymptotic velocity can go up to.
Okay, so I think we can stop here because it's a time limitation. It's not that we are not interested for the topic. So thank you very much.
Gracias.